Welcome back. This week we're going to be discussing basic electricity and then instrumentation and control. So this first video will just be covering the electricity half of this lecture, and then the second one will go over instrumentation and control. So talking about electricity, there's a lot of different units of conversion, and so just knowing some of these abbreviations is going to really be helpful for you if you don't already know a lot of these. So for the electricity lecture, you're gonna, just you need to know that AC is alternating current, DC is direct current, and then kW would be kilowatts. W would be watts, but then in the next lecture, you've got the remote terminal unit control, milliamps, and human machine interface, which you'll get into. So, electricity, right? So, this is the term that's used to describe energy produced by electrons, which flow in a specific direction through a conductor. Right? So your conductor would be that wire, right? That copper wire that, I'm sure most of you are familiar with. And then, hopefully that wire has some kind of an insulator on it with that would be like that plastic covering that goes over it to prevent you from experiencing that electricity. Some of the components that you need to be familiar with, out in the field. So electricity has to be generated some way, somehow, right? Whether it be solar, steam, or gas. Those are your main um, generators for electricity, right? So they're usually turning over a motor, and that is generating the electricity. You've got batteries; those typically use a direct current. There's, to change that, you guys have seen those transformers that, convert the energy from one form to another. Just like a water main, electricity has transmission lines, distribution lines, and then you got your meters to measure the amount of electricity being used. You've got relays that will convert it, and then of course a fuse to protect yourself. So this is all pretty basic stuff that a lot of you, if you, live in a home or, I would guess anywhere, excuse me, you should be somewhat familiar with a lot of this stuff and how it relates to the water industry itself. Two different forms of electricity. You've got static and dynamic. With static, obviously, there's no flow, and then dynamic, it is in motion. So you have two different types of current when talking about electricity. I mean, you've got more, but we're going to discuss just the two basic types, right? You've got direct current, which is it's a type of electrical current where the flow of electrons will move in just one constant direction. Unlike alternating current where, it will reverse. But, you know, direct current is great for like small electronics or something, but it's less efficient over long distance or of like power transmission. So when you're talking about power lines to your house, that's why you're using an AC current. But like your batteries and everything, like I said, that'll work off of direct current. Same with solar, fuel cell. Um, but it means at a fixed level through that conductor, right? However, when you're talking about AC current, right? AC current will change directions or reverse directions periodically. So, like in the United States, we use 60 cycles per second, right? So, every 60 seconds, there's this push in the opposite direction. So, if you're going to equate that to water, um, if you could imagine, water in a pipe being pushed back and forth, not just in one way, right? And that's kind of how the alternating current works. Um, so that's that. So one of the more popular equations used in electricity is this discussion of Ohm's law, right? It is probably the most fundamental equation in electrical circuits. So you have E equals I times R, right? So E is the equivalent of volts, I would be amperage, and then you've got R, which is your resistance, and that's measured in ohms. Um, you could say that the push or the voltage is what's needed to move electric current through a resistor, and that depends on how much current you want and how much the resistor will resist. So let's go over an example of that. Okay, so to dive into, voltage a little bit more, that would be that measure of electrical pressure, right? Very similar to water pressure. There's going to be different, you know, levels or amount of pressure that your electricity is going to have. Very common, standards here. So you've heard 110 or 120 to, the 240, 480. Typically you're going to stay underneath 600 volts. Anytime you go over 600 volts, you actually have to have a certified electrician. I know that there's a lot of people who may be titled as an electrician at their agency, but unless they're a licensed electrician, they're not allowed to touch anything over 600 volts or greater. So, and then you got amperage, and that is that measure of electrical flow or current. So if you don't have any flow, like in a static condition, the only thing that you can measure at that point would be your voltage. And yeah, this is going to be similar to gallons per minute. Anytime you're talking about Ohm's law, you're really talking about this measure of electrical resistance. In water, we often refer to the Hazen-Williams formula, right? Because that measures the resistance of water flowing through your pipes. But that's just a way to equate Ohm's law to the water industry. So anytime you have an increase in voltage or pressure, right, it will increase the flow rate. However, if you have an increase in resistance, it's going to decrease that flow rate, right? Um, so that's all we're trying to measure with Ohm's law. It's just trying to give you this electrical current, and give you a measurement of it. It's how power is, calculated, because it's important to know this when you're trying to figure out pumps, or how much power you have going to your pumps or any kind of facility that does require power. Recently, on one of the engineering projects at VID, there was an issue where they wanted to put in a larger pump than the power that was available. Was at that site, and unfortunately, the engineer who was doing that design missed that detail. He just assumed that there was enough power there to operate this pump, and yeah, that led to some discussions. So that's why we want to know these things. When you take your distribution exams, there's a good chance that you're going to be asked these kinds of questions about wattage and stuff. So that's another reason why we cover it. Um, so you have your watt, right, which is that practical electrical, the unit, right, practical unit of electrical power. Um, and so how do we solve that, right? Well, watts equal E times I, or volts times amps. And I think we got a problem coming up here. Let's see. Here's the equivalents, right? So if you look, you got 746 watts, which is equivalent of 1 horsepower. So 1 horsepower, excuse me, 746 watts. If you were to times that by 1,000, that decimal point would move over 123, right? And you would get 0.746 kW, right? And then, the 0.746 kW is the equivalent of 3,960 gallons per minute per foot. So where does this 3,960 gallons per minute per foot come from? Well, if you were to take the 1 horsepower, which is the equivalent of 550, um, and you were to multiply that by the weight of a gallon of water, which is 8.34, and then times that by 60, so 550 times 8.34 times 60, you get 3,960. So that's where that number comes from. And then, of course, 1,000 watts is equal to 1 kW. At your houses or your apartments, or at least at the one that I lived in, you have an electric meter, right? And so that's usually going to be measured in kilowatts per hour. And so if you had to do a math problem here, like in this example here, if you had 5 40-watt light bulbs, how many watts would you need, right? So 5 times 40 equals 200. So if you were, let's say the power went out and you had a generator, right? And that generator was a 4 kW generator, would it be big enough to run those, you know, 5 light bulbs? So you got 4,000 or 4 kW, which is, if you were to times that by 1,000, you would get 4,000 watts. Here you have the portion of that conversion sheet. Uh, if you were to go look that up, this is the uh, mathematical portion of it for electricity. The only thing I wish they would have done differently on this is that, if you look at how you calculate out your your wire to water formula, it would be the motor horsepower times the brake horsepower times your water horsepower. So for some reason, though, when they set this thing up, they did it in a reverse order here. So a lot of this is stuff that we've already just been talking about. So I'm not going to get too deep into this, but you do have your individual formulas for calculating out your water horsepower, brake horsepower, motor horsepower. Um, but it's just when you're actually going through the entire thing, you're starting with your motor horsepower, then your brake, then your water. See, I think, and then, you can always calculate out, how much money is that going to cost us to operate this pump. So like I say, here's a, little schematic of how that would break down, right? So your motor, brake, and water. You start off, at your motor, right? Your motor is what's got to turn over to be able to move that water. Um, and so, then it goes into your brake horsepower, which is that connection in between the motor and the pump itself. And then, your water horsepower is obviously you're moving that water. So here's just kind of a little breakdown, like I was just talking about. So here you got a nice example of, the a typical problem that you might see on a distribution exam. So if what your pumping capacity is or how many gallons per minute you're able to pump at, and then you know that, you've got the total head that you need to overcome in order to be able to put water into that reservoir, let's say, you could, create a mathematical problem here for you. So you're going to pump 300 gallons per minute to a reservoir 120 feet above the pump. What, how much horsepower will be required? So you would take your 300 gallons per minute times 120, and then you would divide that by the 3,960 gallons per minute per foot. So as you can see, you've got some common units here that you could cross out, and you're left with horsepower. So that would equal to 9.1 horsepower, and that's what's needed to pump up to that reservoir. Here we have a couple more examples. So if had to supply the electrical system to three 75 horsepower pumps, what does that calculate? So 3 times 75, and you get 225 horsepower. Is required to be able to operate those three pumps. But if you had a 4 horsepower pump that operates 12 hours per day, what will be the demand in kilowatts per hour? So you would take that 4 times, we're dealing with kilowatts here, so 0.746 kilowatts per hour. And so you would need 2.98 kilowatts per hour. And then you would take that and times that by 12. So 2.98 times 12, and you get 35.76 kilowatts per hour. So that would be your demand. So that, just quick and easy formula there. But it's a good chance you'll see something like that on your distribution exam. However, you do have your conversion sheet that will, provide you the formulas that you need to solve these if you need it. here we have the just the breakdown on the different types of horsepower that you could be asked to calculate. You get your motor, your brake, and your water horsepower. These formulas come right off of your conversion sheet. This, just gives you a little definition into what exactly it is they mean. Um, so the horsepower required to, an electrical input to the motor, right? That's what's needed to turn over that motor. And then you've got your brake horsepower, and that's the horsepower that's required, for the shaft to be able to turn the pump over. And then you've got the horsepower, to transfer that pump to pump that, liquid up to wherever it is you're going. And this is the last slide for this presentation, but you've got two different phases, right? You get your single phase, and that'll be, what's needed for just a small electric motor, and then you got your uh, triple phase or three phase motors, and that's for the larger stuff. So if you ever see those numbers, it's just to give you a little background on that. All right, that concludes this lecture, and we'll pick it up with instrumentation and controls next.